Every day our cities are buzzing with this hidden logic, right? The flow of traffic, deliveries showing up at our door, people getting to work. But what happens when that logic just breaks? What if we could use AI for more than just finding the fastest route for our car, but to solve some of the biggest logistical puzzles our entire communities are facing? Okay, let's get into it.
Here's a question that probably sounds familiar to a lot of school districts. You've got one school that is just packed, totally bursting at the seams. And then, maybe a few miles away, another one has empty classrooms. How does that even happen? Well, it turns out it's a symptom of a much, much deeper and way more complex problem. And this is what researchers call the school assignment puzzle. Think about it, the challenge of trying to fairly and efficiently place thousands of students into the right schools. It really is a puzzle with a just staggering number of pieces. So take a look at this. It does a great job of showing you the problem in its simplest form. Each of those colored dots, that's a student in a specific grade. Each oval, that's a school. The mission, should you choose to accept it, is to draw a line from every single student to a school. But, and here's the catch, each school has a very strict limit on how many green dots, purple dots, or yellow dots it can actually take.
And it's not just about getting everyone a seat. You're juggling all these competing goals at the same time. Goal number 1, every single student has to have a spot. Number 2, you want to make sure the travel time is as short as possible for everybody. 3, you can't, under any circumstances, go over capacity for, say, 7th graders at one particular school. And finally, to save money, taxpayer money, you want to do all of this using the fewest schools you possibly can. It's a massive, massive balancing act.
So what seems like a simple, administrative headache is actually what computer scientists would call an impossibly hard problem. Let's dig into why that is. Okay, so it has a fancy name, the Student Clustering Problem, or SCP for short. And it's a classic example of what's called a capacitated clustering problem. That just means grouping things together based on where they are, but with hard limits on how big any one group can get.
And that brings us to this really crucial idea in computer science, NP-hard. Now, when a problem is NP-hard, it basically means that as the problem gets bigger, more students, more schools, the time it would take to find the single mathematically perfect solution just explodes exponentially. It very quickly becomes impossible for even the world's most powerful supercomputers to solve perfectly.
And this quote on the slide is just a brilliant way to understand what NP-hard really feels like. Trying to find the perfect school for every kid is like trying to make the perfect seating chart for a giant wedding. I mean, think about it. You move one student to another school, and it seems like a small fix, right? But then that creates a ripple effect. It might push that other school over its capacity, which forces another student to move, which then messes up the travel times for their whole neighborhood, and suddenly you're back to square one, resolving the entire puzzle.
So, faced with that kind of insane complexity, how did researchers even try to tackle it at first? Well, as you can probably guess, the initial attempts, they pretty much hit a brick wall.
They really tried two main approaches. On one hand, you had what's called the exact model. This thing uses powerful software to just crunch the numbers until it finds the one flawless, optimal answer. The problem? It's incredibly painfully slow. Then, on the other hand, you have the greedy heuristic. This one's fast. It works by just making the best-looking choice at every single step. But it's short-sighted. It often gets trapped in a pretty bad solution because it can't see the bigger picture. It's that classic trade-off. Do you want perfection or do you want speed? And this graph tells the whole story. Look over on the left. For the smallest problems, that exact model, the blue bars, it nailed it. Found the perfect solution every time. But then watch what happens as you add more students. The number of perfect solutions it finds just plummets to 0. And that pink line, the error rate, it skyrockets. The model just got completely and totally overwhelmed. So, this failure really paved the way for something new, a much more clever approach. An algorithm that could somehow find that sweet spot between speed and quality. And here it is, meet GRASP. It stands for Greedy Randomized Adaptive Search Procedure, and it's what's called a metaheuristic, which is just a fancy way of saying it's a strategy designed specifically for these kinds of monster optimization problems. And it really does take the best of both worlds. So GRASP has this beautiful two-phase strategy. First up is the construct step. It builds a pretty good solution, and it does it fast. But here's the genius part. It adds a little bit of strategic randomness. It doesn't always pick the absolute best option. It picks one of the top options. And that little trick helps it avoid getting stuck in an obvious dead end. Then comes the improve step. It takes that good enough solution and just relentlessly tweaks it, looking for small improvements, like swapping two students between schools to see if it makes the total travel distance just a little bit better for everyone.
But the real secret sauce, the thing that makes this so special, is that it's a reactive grasp. And that means it adapts on the fly. It's not just running on fixed rules, it's actually learning. If it notices that a certain kind of swap is finding better solutions, the algorithm automatically starts using that strategy more often. It's literally getting smarter as it goes.
Okay, so it sounds great in theory, but how does this clever, adaptive algorithm actually do against the competition? Well, the researchers put it through a pretty grueling test.
They basically set up an algorithm tournament, a showdown. They tested 5 different methods. You had the slow but perfect one called MILP, 2 other advanced methods, and then, of course, our hero, GRASP. They ran all of them on 120 different problems, everything from small, simple districts to massive city-sized challenges.
And their results? They are just stunning. This table shows the average error rate, how far off each one was from the best solution found. For the small problems, okay, most of them did pretty well. But look at the large problems. One competitor was off by an average of 13%. Another was off by 8%. And GRASP? 0. A big fat 0. It found the best-known solution every single time. It didn't just win, it was perfect.
This chart here gives us another way to see that total victory. On this kind of chart, lower is better. It means a more efficient solution. You can see that the green box, which is GRASP, has the lowest median cost. But just as important, look how tight that box is. That means its results weren't just better on average, they were also incredibly consistent and reliable run after run.
So what does this all mean? I mean, we've geeked out on the data, but what's the real-world impact of having an algorithm that can actually solve this puzzle? Well, it matters. A lot. It means using taxpayer money way more efficiently because you're only operating the schools you truly need. It means a fairer, more equitable distribution of students so you don't have some schools overcrowded while others are underused. And for families, it means shorter, safer, and cheaper commutes for thousands and thousands of students every single day.
And you might be thinking, okay, but this is just a lab experiment, right? Nope, this isn't just theory. The researchers took this exact method and applied it to a case study of the public school system in Fortaleza, Brazil. They proved that this algorithm can work with real-world maps, real student numbers, and real school capacities to generate a plan that is just vastly more efficient.
And it really leaves you with a fascinating final thought. If an algorithm like GRASP can untangle the massive logistical knot of assigning students to schools, what other complex city problems are next? Optimizing ambulance routes? Planning out entire public transit networks? Managing waste collection for millions of people? It feels like we're just getting started.